Hello, Mr. Gazza here, Applied Physics Homework 71, Torque. Okay, a few things here. Here's the, all these, a lot of these diagrams when it's like this says the stick is balanced. Okay, that's key. It's balanced with the weight here and the weight on this side. Key formula, torque is mass times the torque arm. Here we go. So this is important. I give you this formula. Torque arm is distance from the fulcrum or pivot point to the force being applied. So in this case, this and this, that's the torque arm here. That's 32 centimeters. The torque arm for weight A is 41 centimeters. That's what that is. Okay? So, calculate the weight of mass B. Show your math in the space below. So, what you need to realize is because the stick is balanced, the torque on this side of the system here, the torque produced by weight A, would have to be equal to the torque of weight B, which we don't know what the weight is here. So that's what we're trying to find. Therefore, so set them equal. So you have torque at A equals to the torque at B. Therefore, if we can calculate the torque at A, and then we're going to be able to use that to help find the torque at B. Therefore, the torque at A, using this formula, is 450 grams times 41 centimeters. Now, I'm making this easy. I'm taking a little liberty with the units. Just bear with me here, please. I think it gets the point across. So I'm going to call the mass of B, mass B times 32 centimeters. Okay, so they're going to be equal. Therefore, if I do 450 times 41, 450 grams times 41 centimeters equals that, 18,450. But before we do that, let's really get the units down. Grams times centimeters. Remember when we did that at the beginning of the year, we were glerfing our units, as we call it. Our units are going to be grams times centimeters, so you can just do that. Grams times centimeters, and our number is going to be that. 18,450, 18,450 equals, basically, it's 32 cm times mass B, which is what we're trying to find. Okay, so then you divide, so you want to go divide this by 32 centimeters, they cancel out, divide this by 32 centimeters, and if you'll see, look at the units first, centimeter over centimeter cancels, I'm left with grams, which makes sense because that's what we want that to be in, and then 8 divided by 32, the answer, I'm going to round it to 576.6 grams, so that's going to be 576.6 grams. That would be the mass that would have to be applied, the weight of B, for this to be balanced. Okay, see how that works? And then here we go. So 2, now we're 2 and 3, we're dealing with this right here. C and D. To get the stick above to a state of equilibrium on the fulcrum, which meaning it will be balanced on the fulcrum. So again, it's balanced equally like we did in class. The weight added to location D would need to be. Alright, so we don't have to calculate. That's 900 grams, but it's a shorter torque arm. And here we have a longer torque arm. And for them to be equal, you have to realize, of these choices here, a lower weight than C. It has to be choice 3. Now the reason is if I put 900 grams out here, longer torque arm, because it's mass times torque arm, this would go down significantly. Much more torque on this system, on this side, than on the C side. Okay? So it needs to be less because the torque arm is more and they're multiplied. So significantly less, actually. Alright? Now, for 3, it says calculate the mass that must be placed at location D to balance the stick above. Show your work. So similar things. What's the torque? So the torque at C equals the torque at D. So therefore, the torque at C is 900 grams times 12 centimeters equals 46 centimeters times X, what we're trying to solve for. Therefore, I get 900 times 12. 900 times 12 equals 10,800 and equals 46 cm times X. Then I divide that by 46 centimeters. Oh, I'm sorry. Let's rewrite this. It's 10,800. Notice grams times centimeters again, so that's our units. It's important to do that. And then if we were to do the 46 centimeters here, they cancel out. Yeah, so we're trying to find grams again, and then that would be divided by 46 240, I'll call it 234.8 is what I'll call it. 234.8 grams is what you have to put there, which if you think about it, right, 900 is closer, but you could balance it with much less weight because the torque arm is much more. Okay? Hopefully you're understanding this. This is about understanding, not just copying off me, because you're going to have to do some on your own right here. Look at number 4. Number 4 deals with this picture here. For a standard threaded nut, turning it counterclockwise will loosen the nut. If the nut in this diagram seems stuck, and is difficult to move, which lettered vector force is most likely to successfully loosen the nut? So I'm trying to rotate it counterclockwise to loosen it. That way is loosening it, and really just make sure you know that just in the real world. The lefty-loosey, righty-tighty thing helps people, but okay, so I need to go that way to loosen it. Therefore, this force, and this force won't work. Which is going to produce the most force? If you look at the vector force, D and B are the same force, okay, but more successfully loosen it, D, because the torque arm of D is more than the torque arm at B. So I'm going to have more loosening force at D, though it's the same, strength applied to it. D. Okay? 5. Calculate the torque produced by weight E. Show your math on the right. So what I'm doing is the total torque at E right here of this part of the system, the downward force produced here, is going to be, use the formula on the front, torque equals torque arm times mass. So in that case it is 18 centimeters times 700 grams, and the total torque at E will then equal that, 18 times 700, and let's do the units first, centimeter times grams, so it's like grams times centimeter, which is the unit, and it is 12,600. It's kind of a crazy number, I know, but that's how you do it. And the torque produced by weight F, show your math on the right. F, the torque is here, further out, less weight though. Here we go. So the torque at F equals torque arm times mass. Therefore, the torque arm here is 64 centimeters times 140 grams. And what you will get is 140 times 64, 8960 grams times centimeter. That's going to be your answer right there. Okay, so this side, maybe you want to write on here, this is the total torque on this side, and the total torque on this side is 8. Feel free to do this. I'm going to encourage you to do this. It helps you and understand this. So that's what we have here. Therefore, based on your answers to the questions above, what will happen to the stick? It will be in rotational equilibrium, be perfectly balanced or close to it. It will move downward on the weight E side. It will move upward on the weight E side. It's impossible to tell from the data. The answer is, because this is more torque here, it's going to go down on the E side. Choice 2. Okay? If they would have to be the same, have to add more weight here or move the same weight out to make it equal. Okay? So, hopefully you can see that, and what I'm going to encourage you to do is, or what you need to do now, is figure out the rest of these, okay, on your own. Use that same basic idea. I didn't give you a lot of space here, I apologize, so just put the math here somewhere. I don't want to see you write too small, but make space for it. If you want to do it on the back, this empty space here, if you have, feel free to do that. I do apologize for that. So this deals with this. 9 and 10 and 11 all deal with this diagram right here. Okay, R and S. And on the back, we have our friend Eddie, who I just put floating in the air. And this is similar to what we did in class. How much force in pounds will Eddie need to apply to the lever to lift a heavy weight? Show your math. So here we have feet, here we have pounds. This is in feet. How much force would he need to apply there to lift this off the ground and make it balanced? Make it balanced. Okay? So good luck doing those, and good luck doing those. Watch this again if you need to. Mr. Gazda, signing off, Applied Physics 71.